Okay, I do promise we are building towards using Laplace transforms to solve a few more differential equations, but we've got a little bit more deriving of formulas to do. Okay, so we have successfully derived multiple ways formulas 2 and 7, which are the Laplace transforms for sine omega t and cosine omega t. Okay, I'm realizing that I numbered things a little bit strangely. That's 2 and that's 7 because when I created the formula sheet, I numbered 1, 2, 3, 4, 5, and then I went to the next column and went 2, 3, 4, 6, 7, 8, 9, 10. Probably should have gone 1, 2, 3, 4, so these would have been next to each other, but I didn't. And I've used this formula sheet in the past, so I've referred to these numbers, so I'm just going to stick with it. Okay, what I want to take a look at what happens if I take the Laplace transform of e to the at times some function y of t, where the Laplace transform here is a known Laplace transform. I'm mostly going to be applying this when y of t is either sine omega t or cosine omega t, because we've seen that an exponential function times sines and cosines shows up a lot, particularly when we're talking about harmonic oscillators. Okay, but I'm going to just derive this in general. Okay, so the Laplace transform of y of t, let me just remind you the notation that we usually use is if we were calling this function y, we're going to call its Laplace transform capital Y, and of course it becomes a function of s. Okay, and of course this would just be the integral from 0 to infinity of y of t times e to the negative st dt. That's just the definition of the Laplace transform. So I want to see now what happens if I take the Laplace transform of e to the at times some function y of t. This formula will now work for any function whose Laplace transform I know. Again, I'm most concerned about what happens if that function happens to be sine or cosine. Oh, and I should have, for both of these formulas, I left out s has to be bigger than 0 for both of these to work. Sorry, omitted that initially. Okay, well, the definition of this is that this would be the integral from 0 to infinity of e to the at times y of t times e to the negative st dt. So it's just my function times e to the negative st. Okay. But now this part and this part are exponentials, so I can sort of combine those. So I can say this is the integral from 0 to infinity of y of t times e to the a minus st dt. But that's exactly what I would get here if I replaced s with s minus a. So I'm claiming that's what I get if I just plug in s minus a to the Laplace transform for y. Okay, let's just double check that. Okay. So, if I were to evaluate y at s minus a, now it always feels a little bit weird when I'm plugging in s minus a for s, okay? So I'm just going to observe that s here is what's inside the parentheses. It's what I'm going to put in that position right there. S is just a placeholder for my input to this particular function. So now, if I have s minus a is the input there, I'm going to be getting the integral from 0 to infinity of y of t e to the negative, this is where I put my input, times t dt. But what was I plugging in as my input? S minus a. Now, notice if I distribute that negative, that's going to make this a negative s and a plus a, which is exactly what we have here. Okay. So it's kind of interesting. Multiplying a function by an exponential doesn't change the basic type of formula we get, but it means that we're evaluating the Laplace transform for this function, little y, we're evaluating its Laplace transform, capital Y, not just at s, but at s minus a. So we're getting a horizontal shift of that exponential function. That's what multiplying by e to the at does. Kind of cool. Makes some sense, because what that does is that affects the exponential function that we're multiplying by y of t. Okay. All right, excellent. So let's now use this to, in particular, see what we will get if we multiply e to the at by sine of omega t. Okay. So what I'm supposed to get is this formula, except I'm going to replace the s with s minus a. So I'm going to get omega over s minus a squared plus omega squared. Now, one thing I notice here is that if s is equal to a, I'm going to run into some problems because this is not going to be defined. Okay. But notice what we had here was that s had to be bigger than 0. Now remember, s was just a placeholder for my input. So if here my input is is s minus a is going to have to be bigger than 0. S is going to have to be bigger than a. Okay. So s minus a here will be a positive number. I'm never going to have a 0 in the denominator. So the restrictions that I have on s, if I have any, in the formula for the Laplace transform of y, become the restrictions that I have on s minus a when I look at the Laplace transform for y multiplied by e to the at. Okay. All right. If I look at the Laplace transform of e to the at times cosine omega t, that's just going to be this formula, but I'm replacing s with s minus a, and that's all the s's. So I'm going to get s minus a over s minus a squared plus omega squared. And again, this restriction on s becomes a restriction on s minus a. So s minus a has to be positive, s has to be bigger than a. Okay. Now, at some point in the homework, I want to say it's question 19, but I'm not sure I've got the number right. You're basically going to be asked to take a look at the Laplace transform of e to the a plus I omega times t, which is e to the at times cosine t plus cosine omega t plus I times sine omega t. So that's another way that you can get the formulas for these two things worked out. You'll be doing this just from the definition of the Laplace transform. I would suggest that when you get to that homework, you do it actually twice. Once directly from the definition, just write out the improper integral that you get and evaluate that improper integral. Then go ahead and do it once using formula 1 for e raised to a multiple of t, remembering that formula 1 as it's given on your formula sheet assumes that we've got a real number here that we're multiplying by t, but we looked and we saw that we could modify it so that instead of the restriction on s being that s had to be bigger than whatever this number was, the restriction was that s had to be bigger than the real part of that number, and then we could go ahead and use formula 1. So I would suggest that you actually work it out just directly from the definition, doing the improper integral, but also use formula 1. Now, using formula 1 is faster. I'm just reminding you that on exams, you can use the version of formula 1 that's given on the formula sheet, which supposes that you have a real number. So if you're going to apply it to complex numbers, you would have to show the work to justify that that can be done, and it's probably simpler to just go ahead and evaluate the improper integral that you get. Okay?